Good morning. It's a nice day in New York City. Kind of mild, not sunny, but very comfortable. Grey skies. Now, this morning we're going to be looking at a little bit of nuclear physics. It's actually not such it's an easy topic, in fact. There are no big equations. Small algebraic relationships is all we've got. However, you have to be able to play around with units. And what kind of units? Energy units and mass units mostly, okay? Now, what we're going to do, we'll do some preliminaries to establish the notation. So those people who know all this stuff are going to get bored for 10 minutes. I'm going to be looking at the periodic table, the build-up of the atoms in the periodic table, and basic notations, okay? Chemical symbols, if you like. So some basics. We look at the electron volt. I actually have a class where I show conversion from electron volts to joules, joules to electron volts. So I'll do a quick version of that too, because it has to be second nature to you. You have to be able to go from electron volts to joules, joules to electron volts in your head, okay? We'll find the mass of the nucleon. We'll use Avogadro's number. Now, experimentally, the mass of the nucleons, the protons and the neutrons, will be slightly different. So we'll use those to calculate binding energy later. Or the Q value of a reaction. What's that? It's the energy produced in a reaction or absorbed during a reaction. It can be exothermic or endothermic. In nuclear physics, they use the word exoenergic. And I just can't say that, it's too hard. The Q value, all right. Atomic mass units. One atomic mass unit is basically the mass of a nucleon. A nucleon is a proton or a neutron. It's the particle found in the nucleus of an atom. The nucleus first discovered by Ernest Rutherford. Is that working there? Ernest Rutherford. Okay. Now, specifically what we're leading up to in this is fission. Fission is the splitting of a nucleus. The word fission was borrowed from biology in the fissioning of cells. I can't remember exactly who borrowed it first. Trying to think. Could be Szilard, I can't remember. We'll look at an example of fission, the fission of uranium-235. That actually makes an atom bomb. So I have to be careful what I say. I don't want to say too much about that stuff. We don't know who's listening, and I don't want to overstep myself into anything classified. And that was first done in the Manhattan District Engineering project, the Manhattan Project, if you like. And it involved three main places in America: Los Alamos in New Mexico, Hanford in Washington State, and Oak Ridge in Tennessee. One place where they developed the techniques of making an atomic bomb, and the other two places which did the hard stuff. What was the hard stuff? One was to get uranium-235, which is a fissionable nucleus, and the other one was to get plutonium, which is also fissionable. What does that mean? It means it can be broken up. Well, specifically, it can be broken up using slow neutrons. That's coming up. So I'll do all of these things, and we'll look at an example of the reaction. There are many different kinds of reactions whereby you throw a neutron at a large nucleus, get two smaller ones, a couple of neutrons, and some MeVs, or joules, energy units. Okay? So that's the first stuff we'll be looking at. So let me clean the board here and do some preliminaries. So what do we mean by preliminaries? Well, basically, the whole universe that we live in, and chemistry, all people who have gone through high school know all this, but I'm just saying it for the record, consists of 92 naturally occurring elements. 92? What about 104? The ones after 92 are not naturally occurring. They're transuranic, as they say. They can be made, but they don't exist in nature. And it goes hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, sodium, and so on. You should be able to say them all the way up to 92. Everybody should know that. It doesn't take long to learn them. That's in order of their atomic number. Hydrogen being atomic number 1. Uranium being atomic number 2. Now, you should also be able to know the main groups. In other words, top to bottom. helium, neon, argon, radon, krypton, xenon. I might have put those last two out of order, but they're the inert gases. And then there's the alkali metals, the alkaline earth metals, and all the various different groups. Now, most of the elements that we have in nature are metals. And there's only a few metals that actually take place in ordinary chemical reactions that make up biology and life. Only a few: carbon, nitrogen, and oxygen mostly. That's a separate idea altogether. Okay. So if we have our elements, our first element, hydrogen. Hydrogen is atomic number 1, and we put a 1 down there. It has only got one nucleon inside in it. This is a simplistic model. The simplistic model that we stick to for this stuff is just the Bohr atomic model, the planetary model, and if the element is not ionized, there's an electron going around this proton carrying a negative charge, and that guy has a positive charge. The proton is much bigger than the electron. 1,830 times the mass of the electron is equal to the mass of the proton. Now, there are things called isotopes. In other words, sometimes we'll have a neutron in there. This is called deuterium. You don't call it hydrogen. And it's a rare isotope of hydrogen. Sometimes you can have two neutrons. And this guy is called tritium. Now that's as far as it goes in terms of isotopes of hydrogen. Helium. There are 2 protons in helium and 2 neutrons. So therefore 1, 2, 3, 4. All of these guys are of the same mass. The atomic mass of helium is 4. We say helium, atomic mass 4, atomic weight 2. Now, the atomic weight is the number of nucleons in the nucleus. It's in atomic mass units. Each one of these guys has a mass of 1 AMU. 1 atomic mass unit. Same for the neutron. Now, we'll probably write this like this. 1 atomic mass unit. And we'll find that today. How much it is, much is in terms of grams, whatever. So, helium has different isotopes too, but most commonly, actually, it's very stable. 2 neutrons and 2 protons makes up helium. Incidentally, if we ionize helium, in other words, if we take away the 2 electrons that will exist in normal helium, we get the alpha particle. The alpha particle is basically a helium nucleus, right? Or an ionized helium atom with the electrons removed. Take away the electrons and you get the helium nucleus on its own. Lithium. Three protons and 3 neutrons means atomic weight number 6. Beryllium. Boron. Carbon. Now you notice something. The number of protons and the number of neutrons are equal so far, except for when we're dealing with isotopes. So these are the normal isotopes of various things such as this. A common isotope of carbon, which you've probably heard about, is carbon-14. Now let's think, how many neutrons exist in the nucleus of carbon-14? Figure it out. There are 14 nucleons, there are 6 protons, so there must be 8 neutrons. So these numbers are just counting things. They identify the element. The number down here identifies its place in the periodic table, the atomic number. I use the word atomic weight. People say mass number. I just don't like the sound of it. When I was a kid, I just learned atomic weight. I left it at that. The atomic number, the atomic weight. So the atomic number is the number of protons. The atomic weight is the number of protons plus neutrons. If you subtract the number of protons from the total atomic weight, then you'll get the number of neutrons in there. And this is carbon-14 that you hear about when it's often used for carbon dating. Carbon dating? Yeah, carbon dating. Okay, now the next thing we need to look at in preliminaries, well, let's look at some others. Let's look at, okay, when you get to iron in the periodic table, I forget the number of it, 40 or something. I should have a periodic table here somewhere, I don't actually. So when you start getting to iron and above iron, then you start getting greater numbers of neutrons than there are protons. And let's deal with the last element. The last element is uranium. The last naturally occurring element is uranium. Beyond uranium we can get, uranium is a planet, Uranus, then Neptune, Neptunium, and then Pluto, plutonium. These are elements that are beyond uranium. So for uranium, it's number 92 in the periodic table. Therefore it has 92 protons. Now I forget which items. There are different isotopes of uranium. Let's do uranium-235. Now the fissionable isotope of uranium is 235. 235? Yeah. How many neutrons in there? Okay, so 2 from 5 leaves 3. 9 from 23 leaves 14. So there are 143 neutrons in uranium-235, the fissionable nucleus, the one I put up there. And so on and so forth. Oxygen, let's just look at or nitrogen. The most common isotope of oxygen has 8 neutrons and 8 protons. So its atomic number is 8 and its atomic weight is 16. Nitrogen, 7. Seven protons and 7 neutrons makes an atomic weight for nitrogen of 14. Okay, so that's enough of that. Let's do now something else. We'll do it the electron volt. Now we'll do the mass of the proton and the neutron. So we clean this. So we'll label it like this. The mass of the neutron or the mass of the proton is 1 atomic mass units. Mass of the neutron, mass of the proton. Let's see what this mass is. Well, we can get this amazingly simply by pure thought. Now a standard nucleus to look at is carbon 12 because it has mostly that isotope is very common. Others have different mixes of isotopes, but carbon 12 we'll use to make a standard for the mass, the atomic mass unit. Now 6.02 by 10 to the power 23 atoms Now, if we take a mole of dogs, right, a mole of chairs, a mole of anything, the 6.02 by 10 to the power of 23 of those things. Doesn't matter what it is. 1 mole is Avogadro's number of particles. Now, to find Avogadro's number, that has to be done experimentally. There are all sorts of tricks and ways to do it. We're not talking about that today. So, how many grams of carbon atom, okay. One mole of carbon atoms is 12 grams of carbon atoms. 1 mole of oxygen atoms is 16 grams of oxygen atoms. 1 mole of uranium-235 atoms is 235 grams of atoms. 1 mole of hydrogen atoms is 1 gram. How about that? 1 mole of helium, 4 grams. Lithium, 3 grams. Beryllium, 4 grams, and so on. So a mole of carbon atoms is 12 grams of carbon atoms. How many atoms in that? 6.02 by 10 to the power of 23. So therefore then the mass of 1 carbon atom is 6.02 by 10 to the power of 23. I did that already. .99 by 10 to the power of minus 23 grams is the mass of 1 nucleus of carbon. Now, the nucleus of carbon consists of 12 nucleons. So therefore then, what's the mass of 1 nucleon? Divide this by 12. If there are 12 nucleons in the center of carbon 12, then the mass of 1 nucleon is 1/12 of this number. And I did that already. Now I converted this to kilograms, so this is like this, look. I hope I got that right. Yeah. So that's 1,000. 10 to the power of minus 3 times 10 to the power of 3 makes this just 1. So the kilogram and this just makes 1. So that's going to be 1.66 by 10 to the power of minus 27 kilograms. So the mass of one nucleon is 1.66 by 10 to the power of minus 27 kilograms, and we'll use that number a lot. We'll call it an atomic mass unit. I'll denote by mu. It's the mass of a proton or the mass of the neutron, and that preliminary stuff we will leave for now. And the next thing we look at is the electron volt.